No, there's no sound of this, and I don't think there's any more sound. Okay, so we don't need sound. Watch this. And tell me what you think. This is an image of astronauts on the ISS, and things float on the ISS. Things don't weigh anything at all on the ISS. They are they're weightless on the ISS. So everybody in chat, tell me why. Why are the astronauts weightless? Look at that. Why is the Razor weightless on the ISS? While we watch the rest of this, you guys type in chat. What's your explanation for this? No gravity, good. Free fall, better. There is no gravity. Keep typing. Don't listen to me. Just keep typing. I'm going to be quiet. Okay, let's see. How many do I have? Okay. Okay, so gravity is the most popular in general. That's the most popular for what you all put. It is actually not right. Let's think about if there was no gravity, and what we learned about Newton's law, and maybe you thought, well, maybe you thought that the ISS has some power to it. It actually doesn't. The ISS, it has some tiny engines for emergency, and they do have to move the ISS sometimes because its orbit is actually what's called decaying, because there is a little bit of friction. It's still, the ISS is just kind of skimming the outer part of our atmosphere. As I told you last Monday, right? You think there's no gravity up there? There is less gravity up there, but all right. If you, in fact, there's that crazy dude who jumped, right? He jumped out of basically a space capsule. He was not that much lower than where the ISS is, right? And he parachuted down. I don't remember what that guy's name was. Some Red Bull stunt. There's plenty of gravity up there, right? That's why when the spaceships come down, right? They come down, they get into our gravitational field. That's why meteors hit us. It's not random. Our gravity sucks in everything. Our gravity extends, and it actually, if you look at Newton's law, it extends to infinity. Right? Let's say this is where we left off and the force of gravity is equal to G times, in this case, it would be the mass of the Earth times the mass of, let's just talk about the ISS, the mass of the ISS divided by the radius squared. So, right, there's no cutoff on here. Now, of course, the further and further away, the weaker it gets. So, you know, it's not a horrible hypothesis that there's no gravity. Let me give you a contrast. When, if you ever saw the old videos of the Apollo capsule, they were far enough from the Earth. They were going to the moon. They were far enough to the Earth so that things kind of float because of lack of gravity. Not no gravity, but lack of gravity. But the ISS has, you know, if the Apollo astronauts had to use an engine to turn around. If they had just kept on coasting, they would have left. They would never come back. The ISS is in orbit around the Earth, just like Newton's cannonball is in orbit around the Earth. That requires gravity. That requires gravity. If there were no gravity, the ISS would fly away. So it's not. It's not because there's no gravity on the ISS. It's weaker. It's about, I'll show you the calculation. The calculation is in our midterm study guide, actually. You just have to kind of add, a couple hundred kilometers to the radius of the Earth. The radius of the Earth is 6,000 kilometers. So it's about 95%. It's weaker, you're right, but it's about 95% what it is on the surface of the Earth. So it's another interesting thing that has to do with our weight and being weightlessness, being weightless. So the correct answer is they're in free fall. So what does that mean? What does being in free fall means? It doesn't necessarily, I mean, it just means that there were no other forces on any of the objects other than gravity. So if you've ever jumped off a diving board, you're in free fall, right? And actually think about this, or it's still warm enough. It was like, what is it, like 85 today? I mean, all the public pools are closed, but if you have a pool that's got a diving board off of it, take a tennis ball with you and fall with it and drop the tennis ball at the same time you jump off of the diving board, and it's going to float right in front of your face. That's what's happening in the ISS. The Razor or the cargo or the astronaut that they were pushing, the astronauts themselves are all in free fall, as is the entire ISS. The ISS isn't doing anything but giving them something to breathe, right? They're basically, they would just be in orbit just like the ISS, and the objects that they are around them are in orbit, just like the ISS. They're falling towards the Earth, but they're moving fast enough in this direction that they don't hit it. They are in orbit. As I said, the ISS provides them with warmth and electricity and radiation shielding and something to breathe. But in a spacesuit, they would do exactly the same thing. There's no engines on the ISS that are making it go around the Earth. And it goes around the Earth something like 17 times a day. So it's really, really whipping around there. Let's talk. So that's when you're weightless. You've experienced this probably if you've ever been on a roller coaster. You feel that weightlessness, and apparently the astronauts feel it also. But apparently it goes away rather quickly. Can you imagine having those butterflies in your stomach the whole time, for the months you're on the ISS? But apparently you get used to it and it goes away. You may have also felt that if you haven't been on a roller coaster, if you drive too fast and go over a bump, when your car kind of catches some air, you feel that on there. You might, if you live in a high rise, and if you live in a high rise and you have a scale, you can actually do this experiment. Probably wait till the middle of the night because people think you're crazy, and you want to be able to go a large number of floors without it stopping. We couldn't even. We did this experiment at UIC because there was a high rise we could do it. Even in Elgin, we don't have enough. There was not a tall enough building there to demonstrate this. But if you live in a high rise, take your scale, and you will notice that not just moving. You have to be accelerating up. If you're accelerating up, you will weigh more, a tiny little bit. If you're going at a constant speed, well, I guess if you're going at constant speed, it'll be your normal weight. But as it's trying to climb floors, it's going to accelerate. You'll weigh more, and as it's going down, you'll weigh more. And the hopefully unlikely scenario, although I guess this just happened to somebody, elevator snaps. then you'll be weightless for the 3 or 4 seconds of the rest of your life. There's a urban legend that if you jump right at the end, then it's not going to kill you. That's not true. It may extend your life for a couple of seconds, but you're going to smash into the concrete at 60, 70 miles an hour. You may survive, but it's not, most people don't. So that's kind of the difference between weightlessness and your weight. But what about your mass? Notice there was no weight. You may have thought, F equals ma is not really your weight. It's actually a demonstration of the force of gravity, is what we kind of call our weight, but it's not really. It's really it's kind of the total vertical forces on us. And so what we really feel is our weight, by the way, when we stand on a scale, and what the scale is really measuring is actually the Newton's third law reaction force. If you push, gravity's pulling down on you, you're pushing down on that scale, and the scale is holding you up, right? And it's reading the amount of force it needs to hold you up. And so if there's no normal force, then you don't really weigh it, and you don't feel it. You feel those butterflies. We have evolved to feel, not really gravity, we're evolved to feel the earth pushing up on us with that same force of gravity. It's an equal and opposite force, so we're not falling. When we're falling, when that goes away, is when we start to feel, we're not missing gravity. Gravity is what's making us fall. We're missing the normal force just pushing up on us. That's what we feel as our weight. But even standing still, that can be different depending on where you are. Your weight in the bottom of if you're on a submarine in the bottom of the Marianas Trench, you weigh a little bit heavier because you're closer towards the center of the Earth. Remember, in this diagram, we're just our M2 here is right on the surface. So if you're closer, if you're further down, you feel more gravity. When you're on Mount Everest, you're a little bit lighter. When you're in the ISS, you're a little bit lighter, but not zero. It depends also on what planet you're on, what object you're on. So your weight, your mass is going to be the same. Your mass is basically how much stuff you have inside of you, how many protons and neutrons, really. I kind of add all those up and weight them with some of the energy counts as mass, as we'll learn in a bit if you don't already know. Not so much in your in the body, but a little bit. But how much you weigh depends on where you are on what planet you're on. On the moon, for instance, you will weigh less on the moon. When you get to go to the moon, you're going to weigh less there. When you get to go to Mars, you'll weigh less. Not as much on the moon. The moon will be the funnest place you probably get to walk on. Other than your ship, maybe you may be weightless when you get far enough away. But you would weigh, 150-pound Earthling. That's how much they would weigh on Earth. Would only weigh 25 pounds on the moon. Let's actually watch a demonstration of that. You've probably seen these astronauts before. They skip around when they're on the moon, not because they're happy, because I'm sure they're happy, but because there's not so much gravity on the moon. Their mass is the same, but their weight, even standing still weight, is different than it would be on Earth. Let me get this in full screen.
Well, in my left hand, I have a feather.
Oh.
In my right hand, a hammer.
Can you all hear that? Again, just a verbal thumbs up. Could you hear the astronaut speak?
I can.
Thank you. All right.
I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Pretty cool, huh?
Mr. Galileo was correct in his findings.
Yeah, that's some normal walking there, because there's not a lot of gravity on there. I guess Neil Armstrong hit a golf ball and just went into orbit because there's not so much gravity there. By the way, did you notice how slow the hammer dropped? The acceleration due to gravity is less there, right? Galileo said it was a constant because Galileo was only on Earth. It is a constant wherever you are, and you're not, and there's what planet you're on. The gravitation, the acceleration due to gravity, the gravitational pull, they're not exactly the same thing, right? The gravitational pull is a force. An acceleration, they are related by F equals ma, and they have that mass in there. And again, the mass kind of cancels out, and that's how these things work. By the way, somebody from another section mentioned this. That video we saw of the bowling ball and the feathers falling at the same rate, that was in slow motion. Okay, the feathers actually fall fast. The bowling ball doesn't slow down, and when it's in a vacuum, if anything, it travels a little bit faster because there's no air resistance on it. If you go back and watch that, there's like a brief 2 seconds where you can actually see them fall in real time. It's the feathers. That most of that picture is in slow motion. The feathers are what's falling as fast as a bowling ball, and so you would see here the hammer. It was noticeably falling slower than if you dropped a hammer on Earth on here. So let's go back and revisit acceleration when it has to do with gravity. Remember, this is right, Newton's first law. Newton's law, universal law of gravity here. And then this is Newton's second law, is equal to ma. The m's cancel, but notice this has the mass of the Earth in it, right? And the radius of the Earth. If you're on a different planet, the acceleration and your weight are going to be either more or less. Depending on the radius of the planet squared and the mass of the planet you're on. So what do we mean? Let's make sure we understand about what we mean by acceleration. Remember, acceleration is not how fast you're moving, it's how fast your velocity is changing. So if you drop, if we have a modern day Galileo dropping a ball off of a building, let's just acceleration 9.8, let's round it up to 10 meters per second squared. That means after you drop it, after 1 second, it'll be going 10 meters per second. After 2 seconds, it'll be going 20 meters per second. After 3 seconds, it'll be going 30 meters per second. And remember, 30 meters per second is roughly, multiply that by 2, will give you miles per hour. 60 miles per hour. So this is why you don't want to jump off of anything that you're going to be in the air for more than a second or so, unless you're going into water. But even then, right, if you jump too high and you hit water, water kind of acts like concrete. You learn that in your physics class. So you really don't want to be, you don't want to be in the air for longer than a couple of seconds, unless you have a parachute or something on it. And again, a parachute is air resistance, overcoming gravity. On there. The force is that the parachute gives a force in the opposite direction of gravity, usually equal and opposite, right? You may think, oh, it's the acceleration is 0. That means well, the acceleration is zero, but your velocity, you're still moving, right? You're just moving at a constant speed. And that's why you have to open your chute at a speed that it's not going to hurt you. Sometimes the wind resistance is so much. If you watch like professional, military or stunt people, when they jump out of an airplane and they hit their chutes, sometimes they'll go up. The air resistance is actually, their chutes are designed that air resistance is actually stronger, and it'll make them go up for a little bit. So our weight, we have a simplification. We can talk about the weight being our mass times the acceleration due to gravity. That's little g on our planet, 9.8 meters per second squared, but our weight would be different again on these different objects. Remember those white dwarfs we were talking about, and neutron stars, those crazy objects that have a lot of mass, but they have an incredibly tiny radius. Look how much a person would weigh on one of those things. You wouldn't, I mean, lots of stuff would kill you, but the gravity would kill you on there. Okay. So far we've talked about circular orbits. The ISS is in a roughly circular orbit. But what happens if you, and we talked about in our on Monday about what happens if you don't have enough speed, right? The cannonball or your rocket, right? If a rocket engine fails, it comes back and it crashes down into the Earth. You have to reach a certain speed to get into orbit. We actually call that the orbital velocity, is the speed you need to actually be in a perfect circle. But what happens if you have a little bit more speed than that? Well, then you will form an elliptical orbit. An elliptical orbit is really, it's kind of like just tossing a ball in the air, only it's on the other side. It doesn't, instead of hitting the ground, it goes on the other side. But notice, this is how Newton really explained Kepler's laws, right? The gravitational force is less up here. It's stronger when you're in there. You need to be going faster to overcome that than you do up here. You can explain all of Kepler's laws with Newton's laws of motion and Newton's laws of gravity. If you give it too much speed, it's kind of like you swinging the ball here, and then this rope is really like gravity, right? If you get it, again, two cases, well, what would happen if you cut this rope? If somehow gravity disappeared, the ISS, for instance, would just go flying off. The Earth, for instance, would not orbit the sun anymore. But if you get something going too fast, you can have what's called an unbound orbit. And that's how the Apollo astronauts are able to leave the Earth's gravitational field. They got going fast enough. It's called the escape velocity, how fast you need to go in order to escape, effectively escape whatever object you're orbiting's pull. These are also called hyperbolic orbits, if you ever hear that. Okay. Objects, you may have heard of Oumuamua. Was a comet that came in from another solar system. It came in and it went around the sun once and it left. All the other comets, actually there was a second one we found a couple of months, about 6 months ago, I guess now. We've had two of those, but all of the other comets in our solar system are bound. It may take them hundreds of years, it may take them thousands of years. Some of them probably have orbits that are hundreds of thousands of years. But they're all gravitationally bound to the sun, and they'll orbit it until one of those objects is destroyed. Just so you can practice the math, how to get newtons out of this, there is here's a couple of examples on how to do it. I'm actually going to go ahead and open up the study guide and kind of put them the math problems on it at least, so you can start to kind of see how we do. Our math problems are going to get more complicated now. This is probably the most complicated math problem we have. You need to be able to calculate the force of gravity given the mass of two objects. This is for the sun and the earth, and so you can just kind of I'll leave that to you. Make sure you can plug these numbers in and find the force of gravity. That is the force of gravity on the sun pulling on the earth. And remember, that is exactly the same force as the earth pulls on the sun, right? The force is exactly the same between those two objects. The reason why the earth moves because of it is the same reason why the earth doesn't move when you step on it and you move, because of the mass difference. And you can actually put those numbers in as well. The acceleration of the earth, it's not very much. It's just really enough to get it to kind of turn and keep in the circle, is 6 times 10 to the minus 3 meters per second. Not a lot, but look at the acceleration of the sun due to the earth. It's 1.8 times 10 to the 8th meters per second. So much, much less, because as massive as the earth is compared to us, remember a person is about 70 kilograms. The earth is 6 times 10 to the 24th kilograms. The sun is another 6 zeros, right? Another 6 orders of magnitude. That is what? That's 1,000,000 times more massive than the earth. But that doesn't mean the force of gravity is stronger between the two. It just means the force of gravity is mutual between the two. The force is the same, the accelerations are different. Fun fact, Jupiter is so massive that it does cause the sun to wobble a little bit. The earth doesn't, but the sun doesn't make, the sun actually moves a little bit as Jupiter orbits it. And that's actually how we discover exoplanets. Is how, not by detecting their planets, but by detecting how they make their stars wobble a little bit. Okay. Gravity also causes, not just makes us fall on Earth, it causes us the tides. Not the way you think, and probably not the way you learned in grade school, or you, this is one of the biggest things that they teach you in school. If they ever mention tides, they talk about the moon pulling on the water. The moon pulls on the water, but think of the mass of all the oceans. Again, yes, 76% of the Earth is covered in water, but again, that it's actually a thinner layer if you consider the whole Earth system, the atmosphere and the water and the actual Earth, the rocky part of it. It's an incredibly tiny bit. The moon pulls on the Earth, and it pulls on the sides of the Earth differently. Remember that the force of gravity depends on how far away you are from an object. So the closer, the part of the Earth that is closer to the moon feels a stronger force than the center of the Earth does, because this part is further away. Notice I don't have any arrows on the water. The water is just following, believe it or not, the shape of the Earth. The Earth actually is like a giant piece of silly putty. The solid rock that we stand on, you all probably know, if not you will know in a couple of chapters, is called a plate. You've heard of plate tectonics. It is literally floating on not necessarily liquid. Some of it's floating on lava, magma, we call it, underground. But most of it is just it's kind of resting on kind of like a snow, like a rocky snow. Kind of like, I mean, it's not quite snow. It's more like if any of you have made slime, right? Or it's like silly putty. It's actually not that hard to deform. And the moon actually deforms the shape of the Earth as it orbits around it, and as the Earth spins, right? When the moon's over here, it stays here basically for one night, and the Earth goes around. That's why we have 2 tides per day, right? If it was really the moon pulling on the water, well, whatever. That's why we have 2 tides per day, not just one. We actually have 2 tides per day. But it's really the Earth is changing. Not that you would notice. The only way we can actually notice it is by seeing the water kind of follows the bulge that is produced in the Earth. The actual shape of the Earth changes because of the moon. And on this side, right, it's really weak. So it's it kind of it's a symmetric pull on the planet. The sun does it as well. The sun pulls on the Earth. It's weaker by about a factor of 1/4, but when when it's either opposing the pull of the moon or helping the pull of the moon, we have different times. If you've ever heard of spring tides or neap tides, those are when the sun is helping. We have spring times. It has nothing to do with the season, and there are the neap tides are when the sun is actually counteracting the pull of the moon on it. It's kind of keeping, notice the moon's pulling this way, the sun's pulling this way, that kind of keeps it in a circular shape. In this case, the sun, it doesn't even matter, right? It can be over here or here. It's not what, you might think, oh, this is kind of counteracting it, but it's really, it gets pulled on both sides because of the differential. An important point besides you not parking your car near the beach or things like that, you got to keep. There are no tides on Lake Michigan, by the way. That's another old wives' tale. Lake Michigan is not big enough. Imagine that. It's not big enough, as big as Lake Michigan is, to actually notice this bulge due to the Earth. But you have larger bodies of water. I mean, it does, but not that you could notice. You need a scientific measurement to actually notice the tide on Lake Michigan. And I mean a tiny measurement. But if you've ever been on either of the coasts, you have to worry about tides. You might have more flooding. If you really live there, you might have flooding during a high tide. And you might park your car further away. But another thing that's important concept here is if you have some silly putty, or even if you made some slime or whatever, you just use dough and you mess around with it in your hands and you pull it apart, right? It gets pulled all different directions during the course of a month. The friction is going to heat it up. The Earth is actually warmer because of our moon. In fact, it's one of the many things that work together that keeps the Earth warm enough to have liquid oceans. We would actually have, if we didn't have the moon near us, we wouldn't have liquid. The moon actually, because of this tidal heating, there's other sorts of things. There's radioactive elements in our core. We'll learn all about this when we have a whole. We have a whole week on the terrestrial planets, Earth, Mars, and Venus, and Mercury. We'll learn, Earth will obviously be our star of that. We'll learn all of the things that keep us warm enough. Our atmosphere, our closeness to the sun, the gravitational, we call this tidal heating from the moon, and radioactive elements in our, just below the surface, all work together to allow us to have just the right temperature. Without any one of those things, we're right on, we're kind of, it doesn't seem like it, but we're kind of on the edge. I think you might be able to get rid of the radioactive elements, but I'm not sure. Another interesting thing about that is the tidal forces actually slow down the rotation of the moon. We already talked about that. That's why the moon is tidally locked, right? We keep using that word tidal heating, tidal locked. That's why we always, it's also called a synchronous orbit. That's why we always see the same face of the moon because of this friction. It's not real, the gravitational pull kind of acts like a friction, and it slows down the spinning of the moon so that it's in perfect sync now. Actually, it slowed down the Earth as well. The moon used to be much, much closer to the Earth, and I'll give it away because you'll probably forget about it, but we're going to learn the moon actually was formed in a collision between another planet and the Earth. And so the moon actually started forming basically in Earth's atmosphere. And it was not the atmosphere we have now. It was way different back then. Kind of the remnants, the Earth got bigger after that collision because its core remained intact, and so it sucked in the material. This other planet was about the size of Mars. We even named it. It's called Theia. The rubble turned into the moon, but the moon was much closer to the Earth. Both of them were spinning much faster. A day on primeval Earth was only 6 hours long. It was spinning so fast after the collision. It was still spinning pretty fast before the collision. It's actually sped up after the collision. 6-hour days, but over the billions of years, the moon has slowed down the rotation of the Earth. Because of another law of the universe, which we're actually not going to get to tonight, we'll save it. That's fine. We have plenty of. We can talk about it next week. None of your homework. Your homework will just talk about the book. So make sure you read about it in the book, and our quiz will just follow this part of the book, part of it. And we'll go into more about the laws of the universe next week. It actually works better after relativity anyway. What was I saying? Oh, the moon was much closer. They were both spinning much further. Because of this tidal interaction, it kind of slowed down the Earth. It's still, and as that happened, because of, I'll say the words, and if you don't understand what I'm saying, you'll understand it after you read the chapter this week. And we'll use this over and over again. Conservation of angular momentum. The reason why why it's easier to balance on a bike and things like that. The reason why figure skaters get faster when they move their arms in. The same kind of thing, only this is the opposite. As they get further apart, they've been slowing down. This is conservation of angular momentum. It still happens to this day. You've heard of leap years, but there's actually, which has nothing to do with this, the leap year just has to go, it doesn't really take 365 days to go around the sun. It's like 365.3, and every 4 years we have to account for that. But there's a thing called a leap second. For people have to, we keep time now with atomic clocks that go to, 0.00000, the accuracy 0.00, I think it's 10 to the minus 6 of a second. So in order to really keep those atomic clocks kind of in tune, or we actually have what's called a leap second. You've never heard of it, but maybe you have. About every year and a half, they add a second to the atomic clocks because the Earth is slowing down to that. And if you wait around, you can actually, if you wait around, you can't quite do this calculation. You can kind of do an estimate back of the envelope estimate, but this is the actual number. In about 4 billion years, the Earth will be tidally locked to the moon. So they will, right now, the Earth is spinning faster, and everybody on Earth gets to see the moon. But when the Earth slows down so much that it'll be in exact sync with the moon, whoever's on the lucky side of the Earth, they'll see the moon, and the people on the other side of the moon will never see the moon, because we'll be spinning exactly the same. We'll be spinning so slow, it'll take a month. Our days will be 1 month. fun fact, we won't be around. We won't be around long enough to see that. There are things that will kill us in between 4 and 5 billion years. Is kind of that's kind of the expiration date on the Earth as we know it. And I'll just leave that fear with you for a while. I will explain that to you eventually. You probably all heard of it, but there's other things too. Okay, so what we've done now, as a human race, basically what Newton did. But again, remember Newton used lots of scientists' thoughts before him. In particular, Galileo, who was in particular influenced by Aristotle. Even though Aristotle, didn't understand friction and thought that there was 2 different kinds of motions, he laid the ground for Galileo, and Galileo laid the groundwork for Newton. By the way, I didn't mention this, but Newton, not only did he do all this stuff, he invented calculus in order to figure all this stuff out. And so you may not like him so much anymore if you ever have to take a calculus class, but he had to invent calculus to understand how gravity worked. But now we have laws of physics that give reason to observations, and to an astounding degree. Remember Kepler's laws were incredibly precise, and now Galileo proved the heliocentric model, and now Newton can explain that motion, not just the code. He can explain that motion, and so hundreds of years later, William Herschel built this giant telescope. This is a 1-story. It's probably not that big. But you see, it's about a 3-story telescope with this giant scaffolding to hold this up. Giant telescope, and he discovered Uranus. And so, for the longest time, they would use the occasional comet to make sure it followed Newton's laws. But now with this new planet, they could really make another test of Newton's laws. Remember, even at this time, the technology to actually test gravity on, you need very precise stopwatches and very precise measuring and things like that. It was still easier in 1781 to test gravity in the solar system. They just had ran out of planets until they found Uranus. This was William Herschel. We'll talk about you have to have the bigger the telescope is, the better it is, the smaller objects you can get. It did not, however, it didn't fit with Newton's laws of motion. It almost did. It was pretty close, but it wasn't precise. It wasn't precise as the other planets. And so this was the first, clink in the armor of Sir Isaac Newton, the metaphorical knight armor. This was the first thing that could refute Newton's laws of motion and gravity. And it was a big deal, and it would take almost 50 years, more than 50 years, for us to figure this out. And the person who figured this out, there were people saying, "Oh, Newton's wrong," or maybe gravity works differently that far away, things like that. People are still saying that now, by the way, but for a different reason. Urbain Le Verrier made an hypothesis. He said, "You know what? Well, we just found another giant planet out there. What if there's another one?" He realized, Newton said, right, these objects don't just orbit the sun. What if there's another object here? The sun's trying to pull Uranus this way. What if there's another planet out here that's trying to pull it further away? That's enough to give it a little bit, its orbit to be a little bit off. And it turned out to be right. His hypothesis told us that there was a new planet. He actually predicted the existence of another planet, and actually told people where to go look for it. Johann Gottfried Gall found it within a year, pretty much where Leverrier told him it would be. And, it's kind of a triumph of the scientific method. We spent 50 years questioning Newton's laws of motion. Turned out to be correct. And we had to make another hypothesis that there was another planet. We discovered another planet before we could actually see it by using the scientific method. This is my last slide, I promise. In 1859, Leverrier, he just discovered himself a planet. He's going to go and check all of the orbits of the planets and see if there's some other planets hidden around that we missed the first go around, or that weren't observable by telescopes. So he found another one. He found Mercury. He didn't find another planet, but he found a planet that we knew about. Actually, the ancients knew about Mercury. You can actually, if you get up ridiculously early in the morning, well, actually, no, you don't have to get up ridiculously in the morning. You actually have to kind of get up right before dawn in order to see Mercury. So, but the ancients knew about Mercury. And Kepler had, Tycho had measured the orbit of Mercury, and Kepler's laws seemed to fit Mercury, okay. But, and this, we have much better technology now in 1859. We can measure those orbits. And again, the outer planets, we have to include themselves in that calculation on where the orbits would be. It turns out if you really even want to do, Jupiter and Saturn precisely, you have to know about all of them. In fact, even the orbit of the Earth, we'll learn, changes because of Jupiter. So with our present technology, if we want to really understand the motions of the planets, we have to include them all in our calculations. But in 1859, they realized that that Mercury's orbit was off. So Leverrier hypothesized that there's another planet there, and it's so close to the sun that's why we haven't been able to see it. Like, he knew it was hard to find Mercury. There's another one there that we just haven't been able to see there because the light from the sun washes it out too much. He actually named this one. He was kind of upset that he didn't name the other one. He named it Vulcan for you Star Trek fans. But there is no Vulcan. There's no planet there. And in fact, Newton's laws do not work for the orbit of Mercury. And this is a preview for our next week's. Our next week is that they don't work that way because space-time is bent. It would take Einstein, the concept of space-time, to understand the orbit of Mercury. So I will leave you with that, doing that. And actually, now that I think about it, the energy part of this chapter is actually not even in the homework until next week. So you're good to go. If you want to skip that part, you can skip that part. It will not be on this week's quiz or this week's homework. But be careful. Next week is tough. All right. Next week is Einstein's theory of relativity. If you got some extra time, you might want to go ahead and finish reading this chapter. Einstein's relativity, as I said, it's briefly mentioned in this chapter, but it's not in there. So I'll open up the content page. Make sure you watch that video. There's it's a long one. It's a 1-hour video. Watch that 1-hour video and kind of go over my lecture slides before you try to answer Monday's discussion. Okay. All right. So that's it for me, Yakin, tonight. Any comments or questions on that? Okay. So let's go through what we need to do. I'll open this discussion back up until, 8 o'clock tomorrow morning. So do it tonight. Well, I won't grade it. Let's make it 10 o'clock tomorrow morning. So if you have not responded to your classmates, go ahead and do that. If you have not answered it correctly, go ahead and do that. That does not count as one of your responses to your classmates. So, I mean, it kind of, if you say, hey, thanks for helping me out, and you give the, then yeah, you can do that. That will count that way. That's fine. So that's due tomorrow before 10 o'clock. Friday before midnight, I want you to make your first post to the Alien Life Forum. And I would highly recommend, if you have an idea of what you want to for your evidence post, just go ahead and stake it out while you're in that area there, in that discussion there. And then, of course, on Sunday, as always, on Sunday we have our homework due and our quiz due. And then before next Monday, have your first responses to discussion 5. Okay. Be well, be good. I'm heading through the mountains. I will be lecturing to you from somewhere, some cabin someplace next week, but I'll keep track of you know, my email and stuff. So if you have any questions before then, go ahead and ask. All right. Anything else? All right. Be well. Thanks for coming tonight, and be safe. And we'll see you next class. Yeah. Have a great weekend.